Okay, geometry, let's continue our talk on lesson 4.4. We're going to focus on angle side now. So let's go to the next slide here. So it says, given that triangle ABC, or given triangle ABC, is the triangle determined by angle A, angle B, and the non-included side AC, segment AC, unique, right? So the idea is the following, right? If I know two angles and a non-included side, is there one and only one triangle that can be made, which would mean it's unique, or are there many triangles that could look different but have those three pieces the same, right? That's the idea. Okay, so the first thing we're going to do here is, again, this is going to be one of those indirect proofs. So again, I apologize for skipping that section, but I'm just walking you through. You'll never have to do this by yourself, all right? So let's assume triangle ABC is not unique. So we want to prove it's unique, so let's assume it's not. So therefore, there exists triangle DEF such that triangle ABC would not be congruent to triangle DEF. But, so with angle A congruent to angle D, angle B congruent to angle E, and segment AC congruent to segment DF. Right, so those three congruent pieces have to remain congruent, but yet there would be another triangle. So again, I will draw this picture. So here's triangle DEF as a visual, right? So DEF. So again, A is congruent to D, B is congruent to E, and AC is congruent to DF, right? So this is why it is angle side for right now. Okay. All right. So what we're going to do here is we're going to use the triangle angle sum theorem. So by the triangle angle sum theorem. So we're going to set up an equation for each of the three angles of each of these triangles. So we would have the measure of angle A, so this is triangle ABC, plus the measure of angle B, plus the measure of angle C would equal 180. And we'd have the measure of angle D, plus the measure of angle E, plus the measure of angle F would be 180. Well, think about this, right? So angle A and angle D are congruent, so they're the same. Angle B and angle E are congruent, so they're the same. So what that means is that angle C and angle F would also have to be congruent. Sometimes this is called the third angles theorem for triangles. But we would have to know that C and F are congruent. So I'm going to put 3 here and 3 here. And now look what I have, right? I have angle 1, side, included side, and then angle 2. I have ASA. So we proved that in the last video, right? So step 3 here, therefore, triangle ABC is congruent to triangle DEF by angle side angle congruence, which we established as one of the ways. This contradicts our assumption. This contradicts our assumption. Remember, our assumption was that there's not a unique triangle, so these two triangles would not be congruent, but they are. Thus, triangle ABC is unique. And we proved it. And there you go. So this should establish angle side as another viable way to prove triangles congruent. So if we take a look here, here is the official theorem. So angle, angle, side, congruence, AAS. So two angles and a non-included side of one triangle are congruent to another triangle. Then the two triangles are congruent. Right? So in this picture here, U is angle 1, V is angle 2, and VW is the side not included. Same thing over here. Angle 1, angle 2, and the side not included. There we go. Okay, so let's take a look at this problem here. It says use triangle congruence. Let's state whether each pair is congruent by SAS, SSS, ASA, or AAS, or if it cannot be determined, right? So in the first one here, I have an angle, I have a side and an angle, I have an angle and a side and an angle. This is ASA congruence, right? That side is in between the congruent angles. Second one here, I have a side and a side, I have a side and a side, I have a side and a side. I have three sides. This is SSS congruence. Down here, I have an angle and a side that's not included. Down here, I have an angle, and a side that is not included. This is angle, angle, side congruence. So that's good. And then down here, I have a side, I have an angle, and a side. So this would be SAS. The angle is included. Over here, though, I have a side, and an angle. This angle is not included. So this angle here is included between the sides. This angle is not or non-included. So because of that, we cannot determine this one. So this cannot be determined. We don't have enough information. Okay, part B now. Okay, let's do a formal two-column proof. So this one says prove that segment FH is congruent to segment JL. Well, these are corresponding parts of these two triangles. So if we can prove the triangle is congruent, then we know that those sides are also congruent. We are given three things. GH is congruent to KL. That's a pair of sides. Angle GFH, so angle F, is congruent to angle KJL, angle K, so angle F, angle J. And angle FGH, angle G, is congruent to angle JKL, angle K, so G and K. So we have a side, an angle, and an angle, right? This is angle, angle, side. We have a side, an angle, and an angle. This is angle, angle, side. These two triangles will be congruent by angle, angle, side. And if they're congruent, then the other three parts would be congruent, and that would be FH and JL. So our proof is done. Here we go. Step 1. Write down all you're given. Segment GH is congruent to segment KL. Angle GFH is congruent to angle KJL, and angle FGH is congruent to angle JKL. And that is given to us. So because we know all that, we know the triangles are congruent, name them in corresponding order. You can just use one of the angle letterings, right? I'm going to use this one. So triangle FGH. FGH will be congruent to triangle JKL, and that is going to be by angle, angle, side congruence, right? AAS. And because the triangles are congruent, all the corresponding parts are congruent. FH is here and here. That should be congruent to JL, here and here. And that is what you want to prove, and that is by corresponding parts of congruent triangles are congruent. CP, CTC. Nice. All right, last problem here, a little bit difficult, so I'm going to do my best here. So it says all sides and angles of ABCD are congruent to the corresponding sides of angles, corresponding sides and angles of A prime, B prime, C prime, D prime. Is ABCD congruent to A prime, B prime, C prime, D prime? So this is an extension of triangle congruence. Now we're trying to extend it to a quadrilateral, a four-sided figure. So we're going to do a couple steps here. All right, so step 1. We're going to identify the congruent triangles. So we know in this picture that triangle ABC is congruent to triangle A prime, B prime, C prime because of side, angle, side, right? Side, angle, side. We also know that triangle ACD is congruent to triangle A prime, C prime, D prime, and that is also by side, side, angle, side. Okay? So we have two pairs of congruent triangles, side, angle, side. So in step 2, we're going to do a translation, right? We're going to translate triangle ABC to triangle A prime, B prime, C prime, so that A corresponds to A prime, or B maps onto B prime, C maps onto C prime. Right? So we're going to take this triangle and slide it to the right. All right. Well, we can do the same thing with ABCD. So let's translate ABCD in the same manner. In the same way, same manner, right? But, and here comes our indirect proof. But assume D does not map onto D prime. We're going to call this new point A. Call the new point E. Call this new point E. So now we've slid this. So A prime is A, B prime and B, C prime and C, but we're going to have this point out here, E. So instead of D going to D prime, we're going to have this fourth point out here, E. Okay. Well, how are we going to think about this? Well, step 4 right here. So we know that triangle ADC is congruent to triangle A prime, D prime, C prime, and would also have to be congruent to triangle A prime, E, C prime. Right? Because if we drag this over here, nothing's going to change about the congruent pieces, so they're still congruent, right? We just don't know if E and D prime match up. So we know that angle C prime, A prime, D prime must be congruent to angle C prime, A prime, E. Right? That's the two angles from these two triangles. Notice here that A prime, D prime, and A prime, E line up. Right? So if those two angles are congruent, right? If these two angles, and A prime, C prime is used both times, so this segment is used both times, then that means that C prime D and C prime E must be in a line. Must be in a line. So this means that E must lie. Must lie on. Must lie on segment AD, A prime, D prime. Well, again, angle A prime, C prime, D prime is congruent to angle A prime, C prime, E. And if A prime and C prime line up, right? So E must also lie on CD. So again, over here, if I use a different color, I'm use green. So if A prime, C prime, D prime, if that angle is congruent to A prime, C prime, E, then again, A prime C lines up, and that means that A prime D and AE must line up, right? Again, we have this CD and CE. So, I'll do it in green. So, E must also lie on C prime D prime. Well, if E lies on A prime D prime and E lies on C prime D prime, then that means that E must be D prime. And because E lies where D prime is, that means that we found a rigid motion. So there's a rigid motion that exists. Rigid motion exists. And now we know that A, B, C, D is congruent to A prime, B prime, C prime, D prime. And there we go. Okay, so again, this book's really appreciate you understanding things and why. So I did my best. Hopefully you caught on to some of that. If not, it's okay. It's just part of your notes. Okay, thanks for watching, and we'll see you next time.